The Earth. It's big, really big. In this section, we'll cover how we came to know just how big the Earth really is. In so doing, we'll build the first rung in the distance ladder that will take us across our galaxy. We'll begin our journey to the edges of the visible universe, very close to home. Here I am in my backyard. This is where we'll begin to build the ladder that will take us to the stars. There's a post. If you want to know how far away it is, the simplest thing to do is to measure the distance with something like a tape measure. If we take a look at this one, it's 7 feet away. But what do you do if you want to measure something that you can't directly reach with something like a tape measure? Like the rock on the other side of the water. For that, we do something called triangulation. Take a point. Measure an angle of 90 degrees. Step off a known amount, say 10 feet. Measure the angle from the second spot, 50 degrees. And triangulation gives us the distance, 12 feet, to that rock from that spot. That combination of direct measurement and angular measurement. In triangulation, we can triangulate everything there is on the planet Earth that you can see. Triangulation is mathematical. The only errors that are introduced are with the accuracy of the angle and baseline measurements. Although tape measures and protractors work okay in the backyard, they are rather crude instruments. They don't scale well to distances beyond the backyard. If we use more accurate instruments, triangulation can take us a long way. A protractor can give you an estimated angle to the granularity of a degree. A circle has 360 degrees. For greater accuracy, we break a degree up into 60 arc minutes. And each arc minute is broken up into 60 arc seconds. This gives us 3,600 seconds of arc in every single degree. Here we see a theodolite. It's a surveyor's instrument that measures angles down to a second of arc. Using industrial instruments like these, we can answer questions like, how wide is the Grand Canyon? And how high is Mount Everest? In 1902, an extended survey of the Grand Canyon was conducted. The survey found that the Grand Canyon is 277 miles long and up to 18 miles wide. In 1856, the Great Triangulation Survey of India established the first published height of Everest at 29,002 feet. The only limits on triangulating the distance to an object are: 1, you have to be able to see the object in order to measure angles to it, and 2, you have to be able to measure or calculate the baseline. These might not sound like serious limitations, but lightning doesn't wait around long enough to take any of these measurements, and you can't see the top of the sky. Methods for finding distances to things like these have relevance for the methods that will take us to the planets and the stars. So let's go over them. For some things, you need to know something about the physical processes at play. For example, how far away is lightning? To answer this question, it helps to know something about what lightning and sound are. For example, we know that a lightning flash is caused by a massive move of electrons across the sky. This creates a vacuum in the air, and thunder is the sound of the air collapsing back into the vacuum. We also know that sound is a wave. The speed of sound is variable and depends on the properties of the substance through which the wave travels. For air, the speed of sound is approximately 0.2 miles per second. So all we need to do to see how far away lightning is to start counting the seconds at the flash and stop at the sound, and multiply the number of seconds by 0.2 to get how many miles away it is. Here we have a 6-second delay between the light and the sound. So the lightning is 1.2 miles away. As we move up the distance ladder, we'll be using knowledge about stars and light waves in similar ways to our use of lightning and sound waves here. For some things, you simply have to go there to find out how far away it is. For example, how high is the sky? It's not something you can see, so triangulation won't work. To answer this, you need to go there or send something there and report back how far away it is. In the beginning, all we could say for sure about the atmosphere was that clouds were closer to the surface of the Earth than the sun, moon, planets, and stars. We knew this because clouds always covered up the surfaces of these objects, never the other way around. Our knowledge in this area didn't really begin until the late 1700s, when high-flying balloons came into use. Here's a scientific balloon launch. High-altitude balloons have been used for over 70 years for atmospheric exploration. They fly at altitudes in excess of 20 miles above the surface of the Earth for days on end. It wasn't until the 1900s that aircraft, rockets, and spacecraft were put to use to travel high into the atmosphere and figure out just how high it went. Turns out that the atmosphere doesn't have an exact top like the lid of a jar. What happens is that the air gets thinner and eventually merges into and then becomes outer space. Here are the principal layers. The troposphere begins at the surface and extends to around 7.5 miles. This is where we get all of the weather, and it is where our passenger jets fly over that weather. The stratosphere extends from the troposphere to about 32 miles. The balloons we discussed fly in this area. The mesosphere extends from the stratosphere to around 52 miles. It is the layer where most meteors burn up upon entry into the atmosphere. The thermosphere extends up to 240 miles and is considered outer space. The air is so rarefied that an individual molecule travels on average about a half a mile between collisions with other molecules. The International Space Station orbits in this layer. Going there is a technique we can repeat for distances throughout our solar system, but it won't take us to the stars. Now, let's find out how big the Earth is, using geometry as a key technique. Around 200 BC, Eratosthenes actually calculated the size of the Earth and came pretty close. Eratosthenes used Aristotle's ideas that 1. If the Earth was round, the Sun would appear at different positions to observers at different locations. And 2. If the Sun were very far away, the light rays would be almost parallel between any two locations. For his two locations, Eratosthenes chose Alexandria and Syene, now Aswan. He knew how far apart these two cities were, 493 miles in today's units. Eratosthenes knew that on the first day of summer, the sun passed directly overhead at Syene. At midday of the same day, using a tower in Alexandria, he measured the angular displacement of the sun from overhead. He found that the angular displacement was 7.2 degrees. That's approximately 1/50th of a circle. Geometry tells us the angle measured at the tower is the same as the angle between lines connecting the two cities to the center of the Earth. This is because when a straight line crosses parallel lines, it crosses them at the same angles. So given that the angle is 1/50th of a circle, the distance between the cities will be 1/50th of the circumference of the Earth. Thus, the circumference can be estimated by multiplying the distance between the two cities, 493, by 50, which equals 24,650 miles. The actual number at the equator is 24,901 miles, so he was only 1% off. This is an experiment anyone can do. In fact, in 2005, it was a science project for a number of schools around the country. I'll point you to details in the credits, in case you'd like to try it yourself. Once we have the circumference, geometry gives us the rest. For a spherical Earth, the diameter is equal to the circumference divided by pi. That's 7,926 miles. The radius is half the diameter, so it's 3,963 miles. The surface area is 4 times the radius squared times pi. That's 196 million square miles. And the volume is 4/3 the radius cubed times pi. That's 260 billion cubic miles. Needless to say, this is very large. A high school teacher calculated the number of students that could fit inside the Earth. It came to 137,188,690 times 10 to the 12th students. This number of students is so large that if you could count one number per second, it would take you more than 4 trillion years to count this high. So you can see, the Earth is very large indeed. Now that we have a feel for how large our planet Earth is, how high the sky goes, and how we measure and calculate these distances, we'll finish the chapter with a look at some of our great cities at night from space and identify their distances from our home base, San Diego, California. Astronaut Don Pettit went to significant lengths to get high-def pictures of the Earth's cities at night from the International Space Station back in 2008. I combined his pictures with the time-lapse photos taken by the crew of Expeditions 28 and 29 aboard the space station in 2011. The space station orbits 230 miles above the Earth. We start with nearby cities. Like nearby stars, these are the most familiar to us. Distances are measured in hundreds of miles. Nearby star distances are measured in trillions of miles. As we move east across the North American continent, distances grow to thousands of miles. Similarly, distances to faraway stars grow to hundreds of trillions of miles. We jump by thousands of miles as we cross the voids created by great oceans such as the Atlantic. This reminds me of the galaxy voids in the structures known as superclusters. Here's one of the furthest cities. From here, because the Earth is round, we start measuring distances to the west. It's interesting to wonder if the same sort of thing could happen if the universe is curved enough to be closed. The distance ladder is a set of techniques for determining an object's distance. Each step works for a particular situation and distance range and supports the steps above it. This is how we work our way from Earth to the stars and on to the most distant galaxies. We have just built a solid first rung for our ladder. We can now use the entire diameter of the Earth, 7,926 miles, as our baseline for triangulating off the Earth and into the solar system. Here's an overview of the rest of the ladder. Parallax is the second rung in the ladder. Direct measurement doesn't work for figuring out how far away the sun is. For that, you use an extension of triangulation called parallax. If you hold your finger up in front of your eyes and close one eye at a time, you see a shift in your finger's relative position with respect to distant objects. This is parallax. It can be used to calculate the distance to our solar system neighbors and nearby stars. All you need for this to work is a more distant star that doesn't move when the target object is viewed from different locations. Parallax accuracy goes down as the distance goes up, and it doesn't work at all for stars and galaxies that don't have more distant objects that remain stationary as the Earth-bound observer moves. For those objects, we use a technique called standard candles. Once we know the intrinsic brightness of a star, we can use the simple inverse square rule with a drop-off in the apparent brightness as the object is seen on Earth. Some objects lend themselves to this technique better than others. Some of the most prominent are Cepheid or Cepheid variable stars, emission nebula, and Type 1a supernova. These methods can take us across the Milky Way, out to nearby galaxies, and into local supergalaxy clusters. The final rung on the ladder is redshift and the Hubble constant. The most distant galaxies are too far away to see Cepheid stars or supernova explosions. For these, we owe our thanks to Edwin Hubble, who discovered a relationship between the speed that a galaxy is traveling away from us and its distance from us. Based on the evidence from an expanding universe, the faster a galaxy is receding away from us, the further away it is. We get the receding speed from the red shift in the light from the galaxy. This method works all the way back to near the Big Bang around 13 billion years ago. We'll be building this ladder rung by rung as we move through the following segments of this video book. In this chapter, we have used direct measurement, triangulation, and geometry to find out how far away things are here on Earth. In the next chapter, we'll use parallax to measure how far away the Moon, Sun, and planets are. We'll take the direct method to measure the extent of the Sun's heliosphere. The next section is our solar neighborhood. Parallax will take us to the stars in our local neighborhood, such as Alpha Centauri and Wolf 359. Going deeper into the Milky Way, we'll add Cepheids, supernova, nebula, supergiants, and globular clusters to work our way across the galaxy. A number of these methods drop out as we move into the local group of galaxies around us. As we move further out, only supernova can be relied upon. Also, we move into distances where redshift begins to work. For the furthest reaches of space, we have only redshift.